Hello, everybody. Today we're going to be going over the automated visual inspection system that we created for quality control using computer vision. My name is Arthur Hochul, and I'm joined by my group members, Boyu Kao and Xiao. So I'm going to be going over the subsystem of the programmable logic controller, also known as a PLC. Boyu is going to be owning the subsystem of the CAD design and mechanical processes for the system, and Xiao is going to be going over the mechatronics and computer vision aspect of the system.
So here's our introduction and motivation. So why are we going to do this in the first place? From our past internship experiences, we found that some of the manufacturing firms still use like human labors to do quality inspection, which is proven to have errors, have low efficiencies, have very high labor cost, and have a ununiform quality standard. So we decided to design a system that leverages computer vision and PLC to automate the quality control for lower cost and high efficiency. And here is a demo video to show you guys how our system works. So as you can see, I'm powering up the system now, and we're inspecting a disqualified part, which is colored gray. And as you can see, it's pushed out. And right here, we're having a good part, which is red, and nothing happens. So this is our system overview. Our system have several components included here, such as the roller, vision camera, solenoid push-off unit, and also the part being inspected. And this is the CAD model of our system. And there are several system highlights that I would like to mention. The first is that we put the motor under the 8020 aluminum bar right here to drive the conveyor belt. And we use a timed belt that is supposed to be here to drive the whole system. And the ball bearings also serves as a simple belt tensioner. And we have adjustable solenoid housing for different sizes and placement of the push-out unit. We have self-aligning roller to prevent belt from going off-center. And at the end, we also put a wooden board below the belt to prevent it from shaking, even in high speed.
So next part, I'm gonna go over the subsystem overview. So as you can see, Raspberry Pi is at the central of our system. It's controlling everything. The camera talks to the Raspberry Pi, sending signals. After that, Raspberry Pi sends signals to the Arduino, which acts as a relay and a driver for the solenoid. And then the Raspberry Pi will talk to the PLC, which will then control the motor driver and then eventually the DC motor. So as far as the computer vision part, we're using Raspberry Pi with a camera. And for the camera, we chose to use Intel RealSense 435i because it can provide RGB, depth sensing, and laser features. We did not actually utilize the full feature of the camera, but it could be done in the future. So as for our algorithm part, we're using just OpenCV on the Raspberry Pi due to its computational limitation. So we're using lightweight algorithms to enable faster and processing compared to large models like YOLO and everything else. And we're just focusing on detecting simple shape and color to maintain efficiency at this moment because of the limitation of the Raspberry Pi. So here is the part we made. So as far as you can see, the good parts is red color, which is a rectangular shaped. And the detection action, we didn't actually put a detection label on the good part because it's good. But for the not good part, we label it red, which is a cylindrical shaped object, which you can see we have a box around it, says kick this out. So And as far as our solenoid, the push-off unit, we're using Arduino as a relay and the driver. So we integrate the Raspberry Pi and Arduino to ensure smooth control of the actuation components. So we managed to adapt to the 24-volt solenoids with the amplifier circuit, which is on the right. So for the safety concern, we designed our circuit to protect the component, protects the Arduino, also the Raspberry Pi. And also for the Arduino part, we're putting a delay mechanism to ensure the accurate timing of the actuation. So here's our circuit on a breadboard. As you can see, it's very messy, and we only use it for prototyping. But finally, we managed to shift everything onto a suitable board, which is a lot cleaner.
And now we're going to start talking about the programmable logic controller. Some of you may not know what a programmable logic controller, also very commonly referred to in industry as a PLC, is. So let's go over that. And that's also one of the reasons why we integrated it into our system, is this kind of serves as kind of an educational component for something that is very commonly used in industry. So this is a good learning experience. As you can see here, the programmable logic controller in our system connects to the motor driver, so it can control a DC motor that is used to power and turn the belt. So this is an example of a PLC in an industry setting. Basically, whenever you're in any sort of industry, name it oil, gas, aerospace, pharmaceuticals, automotive, it doesn't matter. Wherever you have certain types of machines or equipment that need instant responses from the inputs in order to control outputs, or they need specific safety concerns, you want a very robust controller that can take specific inputs and immediately give you some logic that will, control the outputs based on that. And so robotic arms, for example, they rely on these type of inputs in order to control outputs in industry. And so for our project specifically, we use an Arduino Octa PLC kit, which is a pretty robust controller that can also be used in the factory setting. And so the first step that we take was to download the development IDE software, and we do what's called flashing the PLC. Flashing basically refers to updating the firmware on the PLC, which overrides with new data. Think of it kind of like you're overwriting a save file with new data. And this is very important when you first start using a PLC, because it makes sure that everything you use is ready to be used with clean data and new programs, and the versions are compatible for programming. So how do you program in this PLC? Well, this PLC gives you a lot of flexibility, but I think in most industry standards, ladder logic is what's used for most PLCs to program. So how do you read ladder logic? Well, it's read left from right and top to bottom, as can be seen here. And basically how it works is you have specific bits, which are kind of like, you can think of them as booleans, they're inputs, and they can be either true or false. And then the coils, which are all the way on the right, are the outputs, which will turn true based on the values of the bits. If the bits are all based on their logic true, then the coil will turn true. And you can make this more complex with the logic by using certain instructions such as timers, where you wait a little bit of time and then you turn the output true, or counters where you have to count up or count down a certain amount in order for it to turn true. And so basically how we went about this was, the first step was to connect the solenoid valve to the actuate on the lever. And as you can see from this video, this was the preliminary test. And you can see it works. When you click the switch, it will turn on. The issue we encountered though was when we were connecting to the Raspberry Pi, the solenoid would not actually output, or would not actuate, and the reason for that is because the voltage drop was too much. So this was solved by using the transistor circuit and having the Raspberry Pi control it, as Xiao has mentioned earlier. So other than that, the PLC is still used to control the 12-volt motor and is able to adjust the frequency, adjust the speed of the motor required.
So our entire project can really be split into three phases. So as of the beginner phase, we did the CAD design, we programmed a little bit on the Arduino, we did some procurement, and we did mostly the mechanical processes like drilling, taping, cutting the 8020 bars and such. For intermediate parts, we were doing PLC programming and integration, also mechanical design with belt tensioning and self-aligning roller. And I will also set up the SBC, the single board computer, aka the Raspberry Pi. I also program a little bit on the camera as well. So as of our last phase of our project, we did AI-based vision algorithm, and we integrated vision camera to control the solenoid.
So here is our future work plan. The very first tip that I would like to mention is that we would like to use enclosed belt. So far, the current belt we use is purchased from McMaster-Carr. It's a section of belt that we have to connect on our own. We tried different methods like melt and connect them together. We tried different tapes, but none of them works perfectly without affecting the mechanical strength of the belt. And that leads to several problems. The taped section of the belt will acquire more torque from the motor, and also it has a friction problem. So in the future, we would like to use an enclosed belt to solve this problem from the very beginning. And also, we would like to use an offline recollection mechanism. So far, the NG part just got pushed out to the ground, which is not ideal and not very industrial. And we would like to utilize at least a bin to recollect them. Or if we got more budget, we can apply another conveyor belt or even a vibratory bowl to sort them and lead the NG part to the rework station or for disposal. And the third is the light shell and also industrial light source. So right now, our system reserved the place to mount the industrial ring light and a light shell. And if we're got more budget, we would like to utilize those on the system because as Ziao will explain later, we would like to focus more on the small defects detection, which is better than right now the shape and the color detection.
So as far as the future work for the computer vision part, first we could use more advanced detection capabilities by utilizing advanced object detection frameworks or extend the detection to classify multiple defects types like stains, cracks, missing parts. We can go as large as identifying customized parts or as small as identifying even the scratches on metal surfaces. Well, to achieve that, we probably want to do a real-time performance optimization by utilizing more powerful computing resources because a Raspberry Pi really just have a really limited computational power. We could use hardware acceleration like GPU or TPUs. As for the Raspberry Pi, they released the AI hat, which is supposed to be better for machine learning or AI. Or we could use NVIDIA Jetson Orion, which is an advanced version of the Jetson, can be utilized for machine learning. And also, we want to improve our detection in real-world conditions because in a factory setup, we will want to utilize the structural light source to provide uniform illumination. Also, we want to simulate the real factory condition with high-speed conveyors, temperature changes, and background distractions. We want to handle that in the future as well.
Yeah, and then just for the PLC, we were using it as an educational component, but in the future, we should create safety logic, which is very commonly seen in an industry setting as well, such as an emergency button to stop the conveyor. There's also a temperature sensor that comes with a PLC kit that can be controlled in order to monitor the temperature values over time. So we can see the loader's heat with the sensor and then stop it if it gets too hot. And also the OptaPLC comes with Bluetooth functionality, so if we can use the wireless components, then we can reduce on firing. Thank you. These are our references, and we will open the floor up for questions.